Okay, so we're starting our recording. Section 6.4 deals with arc length. And I'd like to go right away to an example here. So let me give you a moment to copy this example down. Okay, so here in this question, we want to find the length of an arc of a curve described by these parametric equations. Okay, so remember, a curve consists of coordinates. And every coordinate, there's an x and a y coordinate. But what you can do, you see, is you can have, let me just write this, let me write this another way, hold on. Usually curves I draw in red. Okay, and there's a direction. So this is a curve C, and every curve, every point has coordinates, and coordinates are x and y. But we can say, well, let x and y be functions of time, or functions of a parameter t. And as the t changes, okay, as t changes, well, based on your formulas, your parametric equations for x and y, as t changes, you generate new coordinates. So as t changes values, let's say as t increases, you generate new points. And when you connect the points together, you get a curve. And the arrow on the curve tells you, as t increases, what direction you're going on the curve. Okay, so how many recall parametric equations from their pre-calculus days? It's normally covered. Well, all right, I'm sure you've seen it before, but let's go ahead and, I mean, hopefully you've seen it before. Let's just go ahead and draw. So Javier's seen it. And, we want to find the arc, the length of the arc described by these two parametric equations that lies between the points 1, 1 and 4, 8. So what would be important for this problem to have? What seems to be important for all the problems in chapter 6? What seems to be important to have? A picture. That's right.
A graph.
That's right. Taj and Ange are right. A graph. So what I'm going to do is I'm going to go to Desmos and show you how to graph these parametric equations. So x equals t squared, y equals t cubed, and let's see, if the points are 1, 1, and 4, 8, what would t range between? With parametric equations, we need to give a range on our variable t.
1 and 2.
1 and 2, that's right. It's exactly right, Ange, because 1, 1, well, if t is 1, 1 squared is 1, and 1 cubed is 1. And when t is 2, 2 squared is 4, and 2 cubed is 8. Okay, so those are these are your limits on t. Okay, so let's go to Desmos, and that's how you figure out your limits on t, the beginning point and the end point. And there's going to be a nice t values that work. All right, so in Desmos here, let me bring it up. Let's see, where am I at? Yeah, here I am. Okay. So let's bring up the Desmos. Okay, there's the Desmos. So here's how, first of all, give me a thumbs up if you're seeing Desmos okay. In the viewer. Okay, thank you, Jan. Thank you, Sandia. Thank you, Ange. Thank you, Javier. Okay, so what I'm going to do here is I'm going to put a left parentheses, and I'm going to put t squared. Okay, that's the x equals t squared. And then I'm going to have a comma, and then I'm going to have t cubed, because y equals t cubed. So you see, those are my parametric equations. And then t goes from 1 to 2. T goes from 1 to 2. And what we have to do, of course, is we have to, well, let's move this graph down a little bit. Maybe zoom in a little bit. Or we could zoom out. But there's your arc. There's your arc, that red arc. Are there any questions so far? All right, well now what do you think the length of that arc is? If you had to guess, and you can't, by the way, use the regular distance formula, right? Because the distance formula is for the distance between 2 points, but that's a straight line segment. So I know that you've learned about the distance formula in your past, but that only applies to arcs that are line segments. This is not a line segment. This is a curved arc. But if you had to sort of make a guess, what do you think would be a reasonable guess for the length of this arc?
X squared plus y squared over square root.
Well, I just want a number. When you look at that arc, that red arc, is the length, let me ask you, is the length equal to 10? You think the length equals 10 for that red arc? Or is that too much or too? Yeah, so that's 10 is too much. Javier's thinking around 7.5. Okay, so we can cut with the grid lines. we're able to get an idea maybe of what a reasonable estimate is. Javier's thinking 7.5. Let's see. Yeah, I think of that. I think that might not be too far off. All right, well, we want to find the exact length of that arc. Okay, so graphing it in Desmos gives us an idea of what might be a reasonable answer. Maybe around 6 or 7, something like that. So, okay, well, we need a formula. So this is the formula for finding an arc, a length of an arc. And this is in the book. They show this formula, section 6.4 in the book. For today's class, I'm just going to write it down. But you have parametric equations: x equals f of t and y equals g of t. Okay, and if you want to find the arc length, and incidentally, you also have that t is between A and B. So the arc length, the formula, is equal to the integral from A to B, Make this a little nicer here. Sorry, let me get this just, I like things to be nice and clean. Okay. All right. So and again, this is section 6.4. This is the arc length formula. It's the integral from A to B, of the square root of dx dt squared plus dy dt squared, and then dt. You're integrating with respect to variable t. That's the arc length formula. And this is where t is a parameter. Note, t is the parameter. Now, when you take calculus 3, multivariable calculus, you're going to learn a like where a space curve or goes in three-dimensional space. There's a length for that space curve too, and you'll have another arc length formula that's just an extension of this. But for right now, our arcs, our space curves, are limited to 2 dimensions. So let's go ahead here. And let's go now back to the problem at hand, and let's go over the solution. Okay, so the solution here, what I've done on the right is I've drawn the space curve, and these here, this information here is really for a TI 83, 84 calculator. If you were to set, you'd have to have your calculator in parametric mode, and you have windows for t, x, and y. And a good window is t goes from 1 to 2 with a scale factor of 0.1, and x and y goes from 0 to 10 with a scale, x max, x min, y max, y min. And then the scale factor is 1. But since you're using Desmos, this here may not be, necessary. But let's talk about this. Now remember, x was equal to t squared. So this means that dx dt equals 2t. The second parametric equation was y equals t cubed. So in that case then, dy dt equals 3t squared. So you see, this is how you get the 2t squared, or the 2t. That's dy, that's dx dt. And the 3t squared is dy dt. That's dy dt. So you're going to square each of them and add them. That goes under the square root sign, right? And so this is your integral that you need to find. Are there any questions on this? All right, well, so we're going to then, we have the integral from 1 to 2. If we take 2t and square it, we get 4t squared. If we take 3t squared and square it, we get 9t to the 4th. Now what we have to do is we have to integrate this. We have to integrate this. And WebAssign will want an exact answer for your homework problems. You're not going to have an approximation. So you want to be doing these problems naturally, just like the first exam, your first exam, you're going to be doing your integration, working it out, showing your work, right? All right, we somehow have to integrate this. We got to find the antiderivative. So this definite integral, what makes it difficult is the square root. But we note that between 4t squared and 9t to the 4th, we can factor out a t squared. So inside the square root, we would have t squared times the quantity 4 plus 9t squared. Now, this integral here, if I put in an additional step, would be the integral from 1 to 2 of the square root of t squared times the square root of 4 plus 9t squared dt. Okay? The square root of t squared, normally the square root of t squared, you would put absolute value of t for that. But since your limits are already positive, 1 and 2, the absolute value of t would be just t. And so that's why we put a t here. And so this becomes your new integral. Incidentally, the fact that we can split the product up, the square root of a product is equal to the square root of product a times b equals the square root of a times the square root of b. And that's what we utilize to get this here. Are there any questions so far? All right, well, now we have to decide. Here we are. Here's this integral. What's the best way to compute this integral? Substitution, integration by parts, partial fractions. What's going to work best? Well, substitution is the way to go. Let u equal, and since you've had practice doing substitution, hopefully when you see these integrals, you'll be able to fairly quickly know what procedure is the right way to solve the integral. Let u equal 4 plus 9t squared. Then du will be 18t dt. And so 1/18 du is t dt. And so now your integral with respect to t becomes this new integral with respect to u. The limits, incidentally, the bottom limit's 13. Okay, how do we get 13? Well, remember, u is 4 plus 9t squared. So 4 plus 9 times 1 squared equals 13. Because the bottom x limit, right, 4 plus 9, that's right, Sandhya. Bottom limit, t limit was 1. Top t limit is 2, so to get the new top u limit, you have 4 plus 9 times 2 squared, and that equals 40. Okay, that's 4 plus 9 times 4, that equals 40. So this is now really just a calculus section 5.5 problem. Let me give a moment here before I move to the next page. Please let me know if you have any questions. Okay, so, all right. So what should we do? What would be kind of a nice thing to do with this integral? What would be kind of a nice thing to do? Take out that 1/18. I agree, Jinxon. So we're going to do that. We're going to do that. That's right. That's right. So, all right, I'll go to the next page if everybody's okay. Okay, so, all right. So the arc length, all right, we bring out the 1/18th. And now really it's a pretty straightforward problem. The antiderivative of u to the half at square root of u is just 2/3 times u to the 3/2. And we have to put in 40 and 30. So the length, if like the exact answer for the length, WebAssign would take this answer, is 1/27 times 40 to the 3/2 minus 13 to the 3/2. But if we wanted to write this in terms of square roots, what I've done here on the right is I've shown you that 40 to the 3/2 power is just equal, it's going to equal 80 times root 10. And 13 to the 3/2 power is just going to be hold on here. This is 13 to the half power raised to the third. That's just 13 root 3. I mean, what that is, if I write it out a little bit, it's root 13 times root 13 times root 13, and that's 13. Let me write it a little better here. Hold on. I like to be sure things are neat. This is 13 to the 3/2 power, which equals, root 13 times root 13 times root 13. But root 13 times root 13 is 13. And that gets me 13 root 13. That's how I get this. Okay. And similarly, root 10 to the 3rd power is just 10 root 10. And so for 40 to the 3/2 power, you get 80 root 10. Now we can, and this is what WebAssign would want. WebAssign wants an exact answer. So, either this answer would be okay, or this answer would be okay. WebAssign will mark it wrong if you don't give the exact answer. Okay, and it would be wrong on the test too, because it wants the exact answer. So fair notice there. Now, one thing I'm going to do, I want to convert. I have my length of the arc equal to 1/27 times 80 root 10 minus 13 root 3. But I'm wondering what that is as a decimal, just because, we thought that the length of this arc, of the arc, should be around maybe 7 or 8 or 6, something like that. So if you get the decimal on this, this is about this value here is about 7.6337. So Javier, I think it was Javier who said 7.5. You were pretty darn close. But that's a nice thing. How many might use Desmos to graph the arc, just to give them an idea of what a sensible answer would be? Does anybody think they might do that on the exam or on their homework? Okay, Anne's thinking about that. And Taj, okay, good. And Jan, good. A no jinx son, do not put a decimal answer. Do not put a decimal answer in WebAssign. Use the exact answer. But what I'm trying to say is, like this answer here, the 1/27 times the quantity 80 root 10 minus 13 root 3. I don't know. I mean, I know the answer should be around 7.5. So how am I going to determine? I mean, sure, if I've done my integration correctly, hey, the answer should be right. Check the answer. But it's kind of nice to convert the answer, the exact answer, as a decimal, just so then intuitively you know if your answer is reasonable. So that's why but no, WebAssign wants the exact answer. But I'm content. I'm happy from a practical sense and that answer is good, because I got an answer that the decimal approximation for that answer is around 7.5, and that is what we estimated would be reasonable for the arc length. Does that make sense? Does that make good sense? Excellent, excellent. Okay, okay. Um, what if we got an answer like this? What if we got an answer like 1/27? I mean, let's look here. Suppose we got an answer of 1/27 times 13 to the 3 halves minus 40 to the 3 halves. What if we got an answer like that? Okay. How would we know that that answer's not right? What's a quick way to know that? That's right, Mario. The answer's negative. Your arc length has to be positive. Okay, so that, you know, sometimes it's helpful to intuitively look at things. I remember on a test I took, I actually I know using this approach helped me get a better grade on a test because you know, I double checked an answer and oh wow, that answer doesn't make sense. You know, it doesn't hurt to intuitive. Sometimes you can intuitively check to see if your answer at least makes sense on fundamental grounds. All right, let's go to one more example here. I want to do one more example. Not this one though. Hold on. Not this one. Yeah. Let's take a look here at this example here. Let me give you a moment to copy. I mean, I'm not saying the previous example, there was nothing wrong with it, but I want to look at this example. Okay. I mean, the example I kind of flew by there. All right, take a look here. Let me give you a moment to copy this example down. Okay, so what might be helpful in this problem? We want to now in this problem find some expressions for the length of the arc of the curve from 0, 0 to 1, 1. Okay, so what might initially be helpful to do with this arc? It's traditionally helpful for these problems from chapter 6. Graph it, I agree. So back to Desmos we go. Back to Desmos we go. One moment. Okay, there's the Desmos. And this is something very interesting. So like for like a TI-8384 calculator, when you graph functions, they have to be y equals. Okay, like y equals this, y equals that. But this function here, y to the 3/2 equals x, you can actually type that as it appears. Y to the 3/2 equals x. And look at that. Desmos graphs it. Desmos graphs it. How many think that's pretty cool? Yeah, it's pretty cool. Pretty cool. Ange likes it. Mario likes it. And incidentally, our limits go from, well, the beginning and end points are 0, 0 to 1, 1. So certainly I could go to the little wrench here and change my, x-axis and y-axis. I mean, the limits from 0 to 1. And y, I think, also will go from 0 to 1. Well, no, it will. And hold on, where'd my graph go? Hold on. Let me check something here. One moment, class. No, it's not doing what I want it to do. Hold on. One moment. There we go. Zoom out a little bit. But y, yeah. Let me ask you this. What's the parameter here? What's the parameter? If x equals y to the 3/2 power, I mean, let's try to do this using the parametric equation. So you're used to t being the parameter, but in this case, x is a function of y. So why don't we let y be the parameter? Okay. So if y is the parameter, yeah. Well, here's what we can do. Let me just try it here. Let me just try it. One moment. Give me one moment here. Yeah. So I'll put a left parentheses, y to the 3/2. So x equals y to the 3/2. And then my parameter is y. Okay, y equals y. I'm trying to see if it'll give me a graph. No, it seems to want, let's see, I guess if I put in t, let me see if we put in t. Yeah, by default, um, the Desmos, to graph a parametric equation, it wants the t as the variable. So what you have to do for y to the 3/2 power equals x, that means that we could let x equals t to the 3/2 and y equal to t, and it would graph the same curve. Okay, it would graph the same curve. In other words, here's what I'm trying to say. Let me go to the whiteboard. So, you have x equals y to the 3/2 power, and this is from 0, 0 to 1, 1. So parametric equations if x were equal to t, then what would y have to be equal? If x, I mean, and we have to honor this curve here. We have to honor it, but we're going to use parametric equations to graph that curve. So if x equals t, what's y have to equal? Well, if x is y to the 3/2, y has to equal t to the 3/2. And incidentally, t would be between 0 and 1. Because when t is 0, that'll start you at the origin. And when t is 1, that'll take you to the, to the end point, 1, 1. So this here is one set of parametric equations.
Professor,
Yes, Ange. And that's
uh,
what Desmos wants if you're going to graph it in Desmos. If you're going to graph that curve, x equals y to the 3/2 power. Yes, Ange.
oh, I said I use for parametric x equal t squared. That way I get rid of the 2 at the bottom. So it's going to be t squared and y is going to be t cubed. Oh,
Well, there are different ways to do the parametric equations. Parametric equations for a curve are not unique. So if you let x equals t squared and y equals t cubed, that would be like that would give you the equivalent curve. It would. But this would work also. This would work also. So that's a good point. That's a good point. All right, Ange. Another set of parametric equations is this. If you let y equal y, then x would equal y. X would equal y to the 3/2 power. And y is between 0 and 1. That's also, you don't have to have t as your parameter. You could set y as your parameter. And if you did that, this here would be an equivalent set of parametric equations to the first set of parametric equations. It's just Desmos appears, if you're going to graph it in Desmos, it appears it wants the variable t for its parameter. Are there any questions so far? All right, let me go ahead and continue with the problem here. Now, I might run a few minutes over. If you can stay a few extra minutes, that would be nice. If you can, I understand, but see if you can stay a few extra minutes. All right, so let's go back to the problem at hand. So you have a problem like this in your homework. So I want to make sure you're comfortable. Okay, so we want to find expressions for the length of the arc of the curve, of this curve. So, all right, method one is you let y be the parameter. If you let y be the parameter, then instead of the standard formula, this is the standard arc length formula where you have t as the parameter, instead of that formula, you would need to use this formula. Because if y is the parameter, then x is a function of y. And so you see, instead of dx dt, okay, you would have dx dy, because you're integrating x with respect to your parameter. And if y is the parameter, then you don't have dx dt, you have dx dy. You have to change the formula. You have to alter the formula a little bit so that because y is your parameter. Similarly, the dy dt, okay, would become dy dy, because the t is not your parameter, the y is your parameter. So it's not dy dt, it's dy dy. And this is going to make then your arc length formula. It's gonna be reduced to then this formula here. The integral from a to b of the square root of dx dy squared plus 1. And you'll see this, it's formula 3 in section 6.4, but I wanted you to see why, how that formula comes about. That's formula 3 in section 6.4. Please let me know if you have any questions. Okay, I need about 5 minutes to finish this up, so if you can stay a little bit longer, that would be great. All right, I'm going to move to the next page if we're good. Any questions? Okay, so this is our formula. So what was x? X was equal to y to the 3/2 power. So dx dy, it would be 3/2 times y to the 1/2 power right here. And so this would be your arc length formula. The integral from 0 to 1 of the square root of 3/2 y to the 1/2 power squared plus 1. Perfectly acceptable to find your arc length that way by treating y as a parameter. Now, if y were a function, see, you have x as a function of y. X equals y to the 3/2 power. So y is a natural parameter. But if you had y as a function of x, then x would be your natural parameter. And there's a formula, when that's the case, you have formula 2 from section 6.4. The second method is to say, well, I like t as my parameter. So I'm gonna change I'm gonna adapt my curve to that. So I can let y equals t, and if I did, then y to the 3/2 power equals x would become t to the 3/2 power equals x, right? That's what it would become. And so then you would use the normal arc length formula, formula 1 from section 4.56, and you would get this as your arc length. Are there any questions on that? How many like using t always as the parameter? How many kind of like that? How many of you like that? Okay, Javier likes t more. D'Angelo does. Okay, well, method 2 then would be for you. Nathaniel and Joseph and Ange, sure. Now, Ange, he's okay with letting y be the parameter in this case, and that's okay too. How many like y being the parameter for this? All right. Well, Ange, it seems you're alone for right now, but don't worry, Ange. I think some folks will be joining you. Don't worry on that. All right, and there's one more comment I'd like to make here on this problem. I have that you could integrate this, no problem. You could integrate it, making a substitution, and you'd want to take the 3/2 times square it. That would get you 9. I mean, this here. Hold on. this here would just equal, 9/4 t. And so you'd be able to integrate that. But here's an important thing. We have two formulas for the length. And if we look at these formulas side by side, even though one has a variable y and the other has a variable t, they're still the same integrand. You see that? So you're going to get the same answer. I mean, they're the same integrand. Kiddist, what do you think? Question on that? Kiddist is noticing that. Okay. Ange, question?
Oh no, sorry, I'll press by accident.
Oh, okay. All right. All right. Yeah, so they're the same. So whether you want to do it, one method or the other method, you'll get the same answer. Are there any questions on that before I stop the recording? Okay, I will stop the recording here.